Now, can you apply the same kind of idea in a physical system? So something called physical equilibrium, meaning that you can also reach equilibrium in a physical reaction as well. Now, here's one example of a physical reaction. If I have started with a flask that has only bromine liquid inside. Now, bromine liquid is very volatile, meaning that the liquid itself will undergo changes into gas, or in another word, will be evaporated into bromine gas. And bromine gas, on the other hand, can undergo condensation as well to change back into bromine liquid. Now, the reaction itself looks like this. You'll have some bromine liquid escape the liquid surface and become bromine gas molecule. And at the same time, you'll have some bromine gas undergo condensation coming back to the liquid. What do you think the concentration of the bromine gas and bromine liquid is going to look like if in the beginning I have started with bromine liquid? Now, apply what we have learned before. Let's draw a graph of the concentration of the bromine gas and the concentration of the bromine liquid. Let's see what it looks like. The concentration graph will look like this, and the red line will represent the concentration change of my bromine liquid, whereas the blue line will represent the concentration change of my bromine gas. As you can see that the bromine liquid, which is something that I started with, the concentration of which has been slowly decreasing, whereas the concentration of bromine gas, where something that I don't have initially, the concentration of that will slowly increase. But at one point, there will be a stop at the change of the concentration. The concentration of both the bromine liquid and bromine gas will remain constant throughout. What about the rate of reaction? What about the reaction that is going backwards, which is bromine liquid forming into bromine gas, and the reaction that is going forward, which is bromine gas forming into bromine liquid? Now, the reaction rate can be plotted on this graph as well. Initially, you will have a decrease of your reaction rate, meaning that the bromine liquid reaction will slowly be decreased, whereas the reaction rate of the forward reaction will be slowly increased as well, because you will have more and more bromine gas in the system. You might notice the explanation of these two things has some similarity and some have some differences. Now, in this reaction, I've started off with a lot of hydrogen and iodine molecule. So initially, I have no hydroiodic acid, but eventually in my system, I'll have all three molecules in my system. I'll have hydrogen gas molecule, I'll have iodine molecule, as well as hydroiodic acid. So in the end, my system has been reached to an equilibrium. On the other hand, in the example over here, I've actually started off with my bromine liquid and then move my way backwards to move into bromine gas. But it depends on the nature of this reaction that's being written. So as you can see that the equilibrium can be reached at both sides. So it doesn't matter about which side you're on. If you have a lot of bromine gas, eventually in your system you will have a lot of bromine. Eventually in your system you will have bromine liquid and bromine gas, and that will be reached into equilibrium as well. If you have started off with a lot of bromine liquid, in the end of your system you'll have bromine liquid and gas presented in your system as well. Now let's take a look at, in general, what is the physical chemical properties in your equilibrium system. So for my reaction, A plus B yields C plus D. Throughout the experiment, when it reached equilibrium, the reaction rate of my forward reaction and backward reactions will be exactly the same when it's at equilibrium. When it's at equilibrium, the concentration of all my product and all of my reactant will be having no change at all. Some people tend to make a mistake, and they tend to think the reactant and the product will have the same concentration, where I have to make a point over here. It's actually wrong. In a lot of equilibrium system, you will have more reactant Or in some equilibrium system, you'll have more product in the end. But as long as your concentration hasn't been changing, that means they have been reached to an equilibrium as well. The color/density and all the other physical properties of your equilibrium system will be kept constant as well during an equilibrium. So once again, the forward reaction rate and backward reaction rate in the end at equilibrium point, which is right over here, will be the same. The concentration when it reached an equilibrium, which is right over here, will remain constant. But as you can see that these two lines hasn't been reached to the same point yet. That means the concentration will not be exactly the same for my reactant and constant. Whereas the color and density will remain unchanged as well. 2 points we need to make a notice. The first thing first, equilibrium can be reached from both sides. So if I have a reaction that have a lot of A and B to start with, in the end in my system I will have C, D, and my A, B. It can be reached from my left side. The same reaction, whereas if I have a lot of C and D to start with, in the end, I will have a lot of A, B, and CD mixture in my equilibrium as well. So my C and D will actually proceed to produce some of the A and B, and A and B will going back to produce C plus D. And in the end, reaction rate will be the same. Concentration will remain unchanged as well. So the equilibrium can actually be reached from both left side and right side as well. And it has to be in a closed system. So there's one point we have to make a notice as well. If it is an open system, that means you can constantly adding things and subtracting things, molecules can escape, that it's very hard for you to reach an equilibrium. Whereas a closed system, the equilibrium will be much easy to be reached as well. We're going to have a learning check. Pause the video for a second and work it out the answer yourself. Okay, so the answer of this question is D. So only the last answer. Make sure you understand why the other answers are actually wrong. So for the first one, between W and Z, the concentration are equal, which is incorrect. Here's a graph that represents the time versus rate of reaction, whereas the X, W, and Z represent the rate of reaction of my forward reaction, whereas Y, W, Z represent reaction of the backward reactions or the reverse reactions as well. So between W and Z, that's the time when the rate of reaction has been kept the same and everything else has to be remain constant. So W and Z, the concentration are constant, but doesn't necessarily mean that the concentration of reactant and product are the same. At point Y, the rate of forward and backward reactions is 0. At point Y, only the rate of the backward reactions is 0. The third answer, between Y and W, the concentration of the reactant is increases. This one is actually incorrect as well, because between Y and W, that represent the concentration of the product will be increased. Okay, the X, Y, and Z over here only represent the rate of a forward reactions. Okay, the next learning check, which statement is always true? Pause the video for a second. The answer is C. So the yield doesn't necessarily mean that it's going to be greater than 50%. The rate of the forward reactions doesn't necessarily have to be bigger than the reverse reaction. Concentration or the amount of reactant product do not change. Forward and reverse reactions will not stop. The forward and reverse reaction will constantly be going on. It's just they have been going on at the same rate, so it looks like they're stopped, but if you go to a microscopic point of view, there actually has been constantly going on. Nothing has stopped. Now, can you answer the following learning objectives? What is reversible reaction? What is dynamic equilibrium? What are the characteristics of chemical and physical system in a state of equilibrium? I hope you can. See you next time.